let's take a look at some more examples using L'Hopital's rule. Our first one, so some of these are going to be a little bit more interesting than some of the other ones we did. This one says, all right, we want the limit as x goes to infinity of cosine of x over x. So when we analyze this, this is kind of a tricky problem because the limit as x goes to infinity of cosine of x actually doesn't converge because cosine is constantly, it's a wave. So as x goes to infinity, it never actually settles on a number. But as x goes to infinity, right, obviously x goes to infinity. So how do we compare two things for which we don't have the same type of indeterminate form? Well, in this particular case, we're not going to use L'Hopital's rule, but we're going to use it insofar that we're going to use techniques that require us to be clever about how we're going to approach these limits. So what we can do is we can say, okay, well, I know this much. I know that no matter what, that cosine has to be, it can't be less than -1, and it can't be more than +1. So if I have two limits, if I'm saying, since I know that that's true, I know that this is also true for positive values of x, which again, we're going towards positive infinity, so it doesn't matter. So since that's true, why don't we take a look at each of these limits? So clearly in this particular case, as x goes to infinity, 1 over x drives down to 0. 1 over x drives down to 0. And that negative doesn't matter because again it's driving down to 0. So since this limit has to be at least as big as 0, and it has to be no bigger than 0, well then the whole thing has to be 0. The answer is 0. That's the idea behind the squeeze theorem, is you're saying, look, if it can't be smaller than this number, and it can't be larger than this number, and those are the same number, it just squeezes it in. All right. Now, this one's an interesting one because it defies what you might think is your original logic. You say, all right, x to the 10th, that's way bigger than x squared. And I know that the natural log also goes to infinity, so clearly this is going to dwarf that, very clearly. So let's take a look and see if we can see if that's actually true. So in this particular case, as x goes to infinity, all right, what I want to do first is I want to apply the power rule for logs. I want to say, okay, that's the limit as x goes to infinity of 10 natural log of x over x squared. Okay. But if as x goes to infinity, that still goes to infinity, and that still goes to infinity. So regardless, you still have an infinity over infinity indeterminate form. So let's take the derivative of the top and bottom. So now you have, this becomes 1 over x by derivative, and that becomes 2x. Now let's multiply top and bottom by x so that we don't have like fractions inside of fractions. We have the limit as x goes to infinity of 10 or 2x squared. So now then we're going to take a derivative, or we don't need to take a derivative. We can see that as x goes to infinity, this bottom gets really large, but the top is fixed. So you basically have 10 over infinity, which is 0, which is a really interesting result. What it tells me is that that natural log function, it just doesn't grow as fast as polynomial functions. Do yourself a favor, do this exact problem, but take like x to like the 1/1,000,000th here, and don't even do x squared. You could even do like the square root of x or something like that. And you'll find that the square root of x will beat the natural log of x to any number. So it's a really interesting way, or interesting result that comes from this. And as you move into more studies in calculus, particularly things like sequences and series, that relationship with the natural log and x to a power and stuff like that becomes even more apparent. So just sort of keep that in mind as you continue to study. So finally we have this. We have x goes to infinity of x times sine of 3 over x. So clearly that goes to infinity, but as x goes to infinity here, 3 over x drives down to 0. Sine of 0 is 0. So you have that infinity times 0 indeterminate form. So we want to rewrite that in a way that's not infinity times 0. So let's rewrite this so we can get like a 0 over 0 form. If I say that that's the limit, x goes to infinity of sine of 3 over x over 1 over x. Right? Because that's like multiplying by the reciprocal, which would be x over 1, and it would work. So that's a perfectly fine way. Now if I look at this, I get sine of 0, which is 0, over 1 over infinity, which is 0. So I get a 0 over 0 indeterminate form, which is good. That means that we can apply L'Hopital's rule. So by L'Hopital's rule, we get, this is cosine of 3 over x. And by the chain rule, we take the derivative of 3 over x and get negative 3 over x squared. And then the derivative of 1 over x is negative 1 over x squared. Now let's multiply top and bottom by x squared so we can kind of get some cancellations. And then note that these negatives are going to cancel each other out. So we're going to get limit as x approaches infinity of cosine 3 over x times 3 over just 1. So as x approaches infinity, 3 over x, so you have like cosine of 3 over infinity times 3. Well, 3 over infinity is 0. And cosine of 0 is 1, so you get 3. So that's how you do that one. You know, again, that 0 times infinity case, what you want to do is you want to rewrite one of those terms in like a denominator so you can get, you know, an infinity over infinity or a 0 over 0. And that's really going to be your ticket pretty much every time.